Hi, everyone. Thank you so much for joining us for our first webinar in our series, NOAA Fire Research from Conditions to Impact. This is hosted by NOAA's Climate Program Office and in partnership with NOAA's Fire Observation Research and Services Team, or FOREST. To start us off, we're going to have Monica Kopach of the Climate Program Office tell us a little bit about this series and its goals.
Thank you, Clara. Welcome, everyone. Welcome to our fire research webinar. As Clara mentioned, it's hosted jointly by our program office, CPO, and Forest team. The goal of this webinar, the webinar series, to really showcase the breadth and depth of NOAA's research on fire. And that includes both the individual contributions that we have across NOAA and as well as the collaboration from different places and with the external research community. And this is really where CPO comes in, since our program office works with all the labs, centers, programs across NOAA, as well as the external science community that we support, and that spans various topics, including fire. So the idea of the webinar is to be comprehensive in scope, even if we don't get to feature all our colleagues and projects, but we hope that quite a few of them will step up. So just one word on fire. Why do we focus on fire? I think it's sort of one of the ultimate motivations to have this webinar that showcases our operational responsibilities to observe and forecast fires, fire conditions, fire impacts, especially on smoke. This is what NOAA is charged with doing, does in operations, and we'd like to showcase that and all the fire research that goes into it. So as I mentioned, the first webinar is a case study of our operational capabilities, and specifically showcases the tools that were available to the public at the time when fire broke out in LA earlier this year in LA. So that affected life and property, and actually included both wildland fires and urban structural fires, and had wide-ranging impacts, including actually on oceans as well. So some of these impacts will also be covered in subsequent webinars, so definitely stay tuned beyond this week's edition. And actually, on that note, yeah, thank you for coming, but I'll let Clara elaborate on how the rest of the webinar series.
Yeah, thank you so much. So my email is in the chat. I would welcome any questions or suggestions from attendees. Future sessions for this webinar series are still a work in progress, and we welcome your input. So please feel free to reach out. So today's session, as Monica mentioned, will highlight NOAA's operational capabilities during the 2025 LA fires. So today we're going to hear from three great speakers across NOAA, and we'll start with Robin Heffernan from the National Weather Service. Then we'll move to Amy Huff from NOAA's National Environmental Satellite Data and Information Service, and finally from Fanglin Yang of the National Weather Service. So during the webinar at any point, please feel free to enter your questions using the question feature on the GoToWebinar, and I'll facilitate Q&A sessions after each presentation. So to start it off, I'd love to introduce Robin for our first presentation. So we'll hear from Robin Heffernan today. She's the National Fire Weather Services Senior Advisor at NOAA National Weather Service and the chair of NOAA's Fire Observation Research and Services Team, or FOREST. So Robin will be giving us an overview of NOAA Fire Weather Science and Services. Thanks so much for being here, Robin, and we can't wait to hear from you.
Thank you, Clara. Thank you for having me. Yeah, today I'm going to go over a bit of a broad overview of NOAA's work that we do on wildland fire, and then you'll kind of get to see a little bit of that more in action with the subsequent speakers and more of the case study from earlier this year. Next slide, please. So we have 3 line offices within NOAA that provide support to the wildland fire community. We have the National Weather Service, of course, and some of its specific programs that are on here and entities are the Climate Prediction Center, giving the longer range forecast that we use for wildland fire, Storm Prediction Center for kind of out the 1 to 2 and 3 to 8 day outlooks. Our weather forecast offices that provide up to 7-day fire-specific forecast as well as spots, and then our incident meteorologist program where we deploy specifically to incidents. Of course, we also have our partners in NOAA's Satellite and Observation Organization, NESDIS, the National Environmental Satellite Data and Information Service, and then also our colleagues at NOAA's research organization, the Office of Oceanic and Atmospheric Research, OAR. And one of their labs, Global Systems Laboratory, specifically doing a lot of air quality work, air quality modeling for wildland fire. Next slide. So when it comes to fire, we know that the factors that drive wildland fire and the construct of what we call the fire triangle that you see on the left hand of this screen, which includes fire, weather, and topography, those have not changed over time. We know that these are the factors that ignite fire and determine its behavior, and of course, the most dynamic of those being weather. Next slide. But what we also know, what has changed over time, are the factors that drive the current wildfire crisis. We know that the long-term aggregate of weather is a pattern that is more dynamic and has frequent weather extremes that increase fire potential behavior, exacerbate post-fire risk, and prolong recovery. We can trace these impacts to vegetative health, growth, and bug and disease infestation that lead to fuel susceptibility, such as trees dying and those such of things, and then lead to extreme fire behavior and also rapid spread. This, of course, is all playing out across the backdrop of continuous new development of housing and urban development in what we call the wildland-urban interface, where communities and the wildland meet, all merging with a history of fire suppression across our country, resulting in increasing impacts across the wide spectrum of areas. Next slide. Increasing impacts are coming into effect as well when it comes to wildland fire across our communities, and not just really across the US, but across the globe. We see that our neighboring countries are running into the same issues we are, that the same history of fire suppression and the same increase in fire potential that we are seeing here. The average annual cost in the US for damages and suppression of wildland fires is around $438 billion. The financial impact from this single type of natural disaster is approximately equivalent to the historical annual budgets of the Department of Commerce, the Department of Interior, the Department of Agriculture, and the Department of Homeland Security combined. In addition to this astounding economic impact of devastating wildfires, other significant effects include impacts to public lives and safety, of course, health impacts from poor air quality, and risks and impacts of utility shutoffs and lack of power. Beyond these are the long-term and sometimes ecologically modifying impacts on watersheds, water quality, and vegetation regeneration. Next slide, please. As the landscape of fire is continuing to change, so does the support we need to provide for both wildland fire and the wildland-urban interface for fire management, as well as land management treatments such as prescribed fire. Our challenge today is learning to live with fire while limiting the impacts of fire on our communities. It's not necessarily to limit fire itself. Go ahead and click enter one more time. Our strength is that everything that we do in this space, in NOAA, is shared mission space, not just across NOAA, but across our land management agencies, emergency managers, public safety officials. All of this is shared mission space down to the phenomenon itself, which is fire. Next slide. How we meet this challenge of learning to live with fire is to amplify our strength, which is true collaboration, where each participant of the coordination looks at the problem through the lens of our agency missions to build an outcome that we all own together, regardless of agency jurisdiction. This starts with integration of our data and projects, like the National Emergency Response Information System from the U.S. Fire Administration, as well as the Wildland Fire Enterprise of the Interagency Data Management Enterprise. We need to transition from single agency production of services to co-production of services with interagency partners. These services need to be interdisciplinary across sciences, both physical and social, and comprehensive of the entire fire environment. Currently now, when we look at that fire behavior triangle, we provide services, we and other partners across the fire environment provide services for each leg of that triangle uniquely. And every fire manager out there has to take those pieces of information and put it together to see the whole picture. An interagency production of fire environment services would allow us to provide that picture for them. And in doing so, we would meet the tenets of the Wildland Fire Cohesive Strategy, which is how land management agencies go forth in doing their land management work as well as wildfire work, and our efforts to support them in doing that. Next slide, please. We understand that fire is a natural element of our ecosystem and that the management of land, including fire, is a continuum. NOAA fights fire with science services, providing science-based decision support products and services for all phases of the wildland fire life cycle, meaning before, during, and after, and the continuum of such. We start with the impact we want to make and the information that we need to inform decisions that will get us there. Then we work backward for that information and we identify any gaps of either science needs or general information that we need to collate together to be able to inform those decisions. These critical gaps are what we use to inform our research and development improvements and then work forward through advancing the cycle and ultimately leading to a better outcome. That is our goal. Next slide. NOAA support for wildland fire starts long before the fire does. Next slide, please. With monitoring of drought and fuel conditions, climate assessments, and seasonal outlooks, all of which help to determine the timing and severity of anticipated fire activity. Pre-ignition support combines fuel and weather conditions to provide fire weather forecasts, site-specific spot forecasts, and hazard products such as fire weather watches and red flag warnings. These products inform users that if a fire ignites in the warning environment, it will likely grow quickly and be of safety concern to first responders and the public in the area. It also can warn of the possibility of multiple new fire ignitions due to lightning. Fire detection support utilizes the latest technology of polar and geostationary satellite imagery to detect fire starts and monitor radiative power and fire growth. This imagery has been a game changer with respect to fire intelligence information as well as smoke tracking. Wildland fire forecasting decision support incorporates the latest technology with regard to fire atmosphere coupled modeling and smoke modeling and makes these tools available to incident meteorologists on the ground at the fire location. Incident meteorologists, or IMETs as we call them, work hand in hand with the incident management team to inform fire management decisions with weather information. As we know, the impacts of wildland fire extend far beyond when the fire is out. NOAA support continues in the post-fire phase, utilizing the latest remote sensing technologies to map burn scars, so forecasters can monitor these areas for potentially heavy rainfall and warn for deadly debris flows. Next slide, please. Emerging advancements include fire detection capabilities that enable notification of fire starts to authority agencies for more rapid initial attack response. Initial attack is what we call the first resources that show up to the scene on a fire and start protective actions. The National Weather Service is currently evaluating best practices from our field offices to develop a uniform set of policies, products, and services for fire detection notifications and alerts with partners nationwide. All fire detection notification processes start with partner engagement prior to the dangerous fire conditions or ignitions. This starts with interagency review of annual operating plans and development between National Weather Service local offices and local land management and emergency management partners. The fire weather hazard workflow begins with the Storm Prediction Center fire weather outlook here displayed on the left here for days out to days 8 for preparation and pre-positioning of resources through our land management agency partners, down to more near-term fire weather watches and red flag warnings. During periods of hazardous fire weather conditions, weather forecast offices can utilize the NESDIS Next Generation Fire System to assist in monitoring satellite information to identify new fire starts. Once a new fire start is detected, these offices can issue a notification and proactively issue a site-specific spot forecast to be sent out to the partners to notify them of the fire's likely location and the weather conditions in the area. In environments conducive to intense fires, previous demonstrations have shown that new fire starts can be detected, typically by geostationary satellites, in as early as 1 to 5 minutes, with notifications to partners with an additional 5 to 10 minutes. And this is during a period when minutes matter. Next slide, please. Other change agents include the new NOAA Fire Weather Test Bed, which has been established through Disaster Supplemental and Infrastructure Act investments and is a huge step in the transformational direction of wildland fire and the wildland fire environment as a whole. While the test bed lives in NOAA, it is much bigger than NOAA, and it is serving as an interagency evaluation platform to evolve high readiness fire environment science and technological advancements for operational deployment. The Fire Weather Testbed brings together practitioners across science, land, fire, and emergency management with technological developers through experiments that have been carefully designed and evaluated through social science expertise. The testbed fills a long-term gap that existed in the fire community and serves a foundational role in the research to operations pathway. The first in-person experiment was hosted last June and evaluated the integrated warning team approach that builds upon the satellite-based fire detections that we just talked about and moves it into an interagency integrated approach to fire warnings and evacuation notifications. This upcoming season's experiments include the use of a cloud environment to host a high-resolution downscaled model of wind forecast called Wind Ninja that's widely used in the wildland fire community, as well as undertaking some verification studies across different platforms. This is just an example of the types of efforts we must continue to invest in as an interagency community to move us forward to being able to provide those comprehensive services across disciplines, across agencies, and across departments. And next slide. And that just kind of gives you a broad overview of what we currently do in wildland fire across NOAA and across all of the entities that play a very important role in that, as well as some of our upcoming new approaches and where we look to go forward in service to the wildland fire community, the public, and the wildland fire enterprise as a whole. Thank you for your time today.
Thank you so much, Robin, for that great presentation. I'll invite all of our attendees to please enter your questions into the question feature of the GoToWebinar control panel. We do have a question coming in for Robin. What is the minimum size of a fire in order for it to be detected from your remote sensing?
So we have had fires as small as the size of your dining room table be detected by geostationary satellite imagery. In general, we're typically looking at things that are on the order of 5 to 10 acres.
Great, thank you. Folks, if you are listening and you have a question, please feel free to put that in the question feature. I'll give it another minute or two. And if you think of a question past this Q&A period, please still feel free to enter it into the question feature and I'll pass it along to the appropriate speaker. So I'll just give that one more minute.
And I will say, you guys feel free to reach out to me with questions that come up later on. I'm happy to address them at any time. I have the typical NOAA email address, my first name dot my last name at noaa.gov, so you know where to find me.
Great. All right, thank you, Robin. For the interest of time, we will move on. And I would love to introduce our next speaker. So next we will hear from Amy Huff. Amy is a senior scientist at NOAA NESDIS Center for Satellite Applications and Research, or STAR. So let me allow Amy to share her screen. So today, Amy will be talking about NOAA satellite observations during the 2025 LA wildfires. We're really excited to hear about this work, Amy, so go ahead.
Great. Thank you so much, Clara. Is everyone able to see my screen?
Yes, we can see it.
Okay, super. So thanks for that kind introduction. I just wanted to mention I'm a member of the Aerosols and Atmospheric Composition Science team at STAR. And even though I'm going to be presenting today, the products that I will be talking about, the satellite products, have been developed by colleagues on my science team as well as the fire science team. So it's a real team effort to develop these products. Okay, so NOAA has two basic types of satellites, and they are based on the orbits of the satellites. So the first, and probably one that's most commonly known to people that they're familiar with, are the geostationary satellites. These are administered by NOAA's GOES-R program, and these are the weather satellites. So they're used to monitor, severe storms, tornadoes, hurricanes, that sort of thing, fires as well, of course. And so the satellite is in a high altitude orbit, and the orbital speed of the satellite matches the rotational speed of the Earth. So you can see in the first little animation here, the geostationary satellite. So it's continuously observing the same area or the same hemisphere of Earth. And so that allows it to have nearly continuous observations. And that's why it's useful for weather forecasting. But the limitation, the drawback of these types of satellites is that the instruments tend to have coarser spatial resolution, meaning when you look at the satellite imagery, the pixels look larger. And I'll show examples of that. And so these geostationary orbit satellites, they're abbreviated as GEO. And the key instrument on the GOES satellites is called the Advanced Baseline Imager, the ABI, for monitoring fires and smoke. So then the other type of satellites, shown in the schematic on the right, are called polar orbiting satellites. And they're in a low Earth orbit, so that's abbreviated LEO. And NOAA's polar orbiting satellites are administered by the JPSS program. So these are research satellites. They're in, as I said, a low Earth orbit. And what that means is that they're orbiting around the north and south poles, as you can see in the animation. So every time the satellite makes a complete orbit of the Earth, it's observing a new area of the surface. So that allows the polar orbiting satellites to have global coverage. And also the instruments tend to have higher spatial resolution or smaller pixels when you look at the satellite imagery. But the drawback is that because there's global coverage, there's only typically 1 to 3 observations per day for the same location on Earth. And if there's more at high latitudes because of the way the Earth is shaped and the fact that the satellite's orbiting over the north and south poles. So the key sensor for the NOAA polar orbiting satellites is called VIIRS, the Visible Infrared Imaging Radiometer Suite. So I first want to show you observations of fire radiative power for the Los Angeles wildfires. Now, this was one of the products that Robin mentioned. So for all of the examples of the satellite imagery, they're all from the same day, which is January 9th of 2025. And the time period for the geostationary satellites on the left is from 19 UTC to 21 UTC. And so that corresponds to 11 a.m. to 1 p.m. local time in Los Angeles. And then on the right is the polar orbiting satellite example. This is from the NOAA 20 polar orbiting satellite. And this observation was taken at 2048 UTC. So that's about 1:48 p.m. or sorry, 12:48 p.m. excuse me, local time. So a few things hopefully will jump out right away. The fire radiative power, that's indicated by these yellow, orange, and red little pixels. They're little squares. And so, of course, with the geostationary satellite, we're getting observations every 1 to 10 minutes of fire radiative power. And fire radiative power, it's telling you the rate of emitted radiative energy by the fire at the time of the observation. And it's the most important measurement for determining the area of most intense burning. So the darker the pixels, the darker the red and orange colors means more intense burning areas of the fire. And of course, on the backdrop, we have the visible imagery from the satellite. It's actually a combination of the red, green, and blue spectral bands of the satellite. But ABI doesn't have a green band, so that's simulated. So with that visible imagery, you can really see the thick smoke that was being emitted by the wildfires during this particular period. So again, the geostationary satellite, we're able to see the movement of the smoke, the growth of the intense burning of the fires. but the pixels, you notice they're significantly larger compared to the geostationary, the VIIRS observation on the right. So of course, the VIIRS observation is static. It's a snapshot in the early afternoon local time, but you can see those little fire radiative power pixels are much, much smaller. So we're able to see more detail in terms of where the fire is burning and where the most intense burning is occurring. And also we can see, just in terms of the smoke plume, more details in terms of the contours and thickness of the smoke. All right, so we have from our group a couple of satellite products that are most commonly used for smoke. So I'm just going to talk a little bit about them here just to give some background, and then I will show examples for Los Angeles fires. So on the top right here, this is just the true color or that visible imagery from the polar orbiting satellite. This is from September of 2020. And so I hope you can see the kind of thick grayish colored smoke that's stretched all the way across the continental United States on this day. So the first product is aerosol optical depth. That's a quantitative measure of aerosols. And because it's quantitative, it can be used to estimate surface air quality conditions. And I'll talk about that product in a few minutes. But aerosol optical depth, the thing to remember, it's unitless. And so the higher values correspond to higher concentrations of aerosols like smoke. So in the lower left here, we have an example of the aerosol optical depth. And anywhere you see the bright red and orange colors, those are higher areas of aerosol optical depth, and they correspond to higher concentrations of smoke aerosols. So the other product is on the lower right here. This is called aerosol detection. It's also called the smoke or dust mask. It's a qualitative indicator of smoke and dust in the aerosols in the atmosphere. And the reason why it's useful is because sometimes this example of the smoke is quite obvious, but sometimes smoke is more diffuse. So the smoke mask helps draw your eye to areas where smoke or dust is occurring. All right, so first, here's the examples of the aerosol optical depth for the Los Angeles wildfires. And this is the same day and time as we saw for the fire radiative power. And again, on the left is the geostationary satellite observations. And you can see anywhere where there's the dark red and orange color, that indicates the thickest smoke, the highest concentrations of aerosols. And so for aerosol optical depth, we have observations every 5 minutes. And again, you can see it looks more pixelated, right? The spatial resolution isn't quite as high. So, some of the fine features of the smoke, are kind of blended together. Whereas on the right, we have the VIIRS observation from the polar orbiting satellite. And again, it's only a snapshot. We're just getting one observation in the early afternoon, but you can see, because of the higher spatial resolution, the very fine detail of the smoke and where the thickest aerosols are located. And similarly for aerosol detection, again, on the left, we have the geostationary satellite observation. And one difference with aerosol detection is that with the geostationary satellites, we're only getting information about the presence of smoke or dust. So in this case, that lavender shading is indicating that the satellite is sensing smoke. And in contrast, on the right, with the polar orbiting satellite observation, because VIIRS has more spectral bands and more types of radiation wavelengths that it's measuring, not only do we get an indication of the presence of smoke, but also an idea of the relative thickness. So this shading here, the kind of lighter pinky purple lavender colors to the darker magenta, almost red colors, indicate the relative thickness of the smoke. So thin versus thicker smoke. So where we have the kind of magenta shading in the middle of the plumes, that's indicating thicker smoke. And then the lavender colors on the periphery of the plume is indicating thinner smoke. All right, so I mentioned surface air quality. So the reason why smoke is an issue for in terms of air quality is because it contains high concentrations of fine particles or particle pollution, which is also called PM 2.5. These are very, very small aerosols, and the reason they're hazardous is because when you breathe them in, they can penetrate deep into the lungs and actually pass into the bloodstream as well. So US EPA has developed this color-coded air quality index, it's called. So you'll see the different colors here, the shading. And the thing to remember is if you see orange, red, purple, or maroon shading, US EPA wants you to take action to limit your exposure to the smoke. And so again, we have the PM 2.5 estimated from the geostationary satellite observations on the left, and then from the polar orbiting satellite observations on the right. And again, the difference is we have the more frequent observations. These are 1 hour average PM 2.5 surface air quality estimates from the geostationary satellites. So again, that helps you see kind of how the smoke is impacting surface air quality in not quite real time, but certainly updated on an hourly basis. And in contrast with the polar orbiting satellite, we're getting an estimate of the surface air quality for the whole day, so a 24-hour average. All right, so just to summarize, the NOAA satellite imagery provides vital information during wildfires. And so not only do we have obviously, emergency managers and fire experts, as Robin discussed, using the satellite imagery, but we have air quality forecasters, National Weather Service forecasters, and even just the general public will consult it just to understand what the conditions are in their area. So I talked about 4 different fire and smoke products, including fire radiative power, which gives the location and intensity of burning areas, aerosol optical depth, which is a quantitative measure of smoke, the aerosol detection smoke mass, which is a qualitative indicator of smoke, essentially indicating the presence with the geostationary satellite and both the presence and relative thickness of smoke with the polar orbiting satellites. And then also surface fine particle PM 2.5 air quality. This gives an indication of basically telling you when you want to limit your exposure to smoky air. And so hopefully you'll take away from this the idea that the products from the geostationary satellites and the polar orbiting satellites, they're complementary. They both have their strengths and limitations. So with the geostationary satellites, we get nearly continuous observations, so we can track the growth of fires, where the most intense burning is occurring, and also the movement of smoke plumes. And then the polar orbiting satellites have very high spatial resolution, and they allow for observations of details of the fire gradients and the active burning, and then where exactly the smoke is. And then last I wanted to mention, so if you're interested in look at some of these different products on your own, we have near real time and archived observations from the geostationary and polar orbiting satellites. All the products I showed you today are available from our group's Aerosol Watch website. And so all you have to do is just enter into your favorite search engine, NOAA Aerosol Watch, and it should be the first result that comes up. And so you'll see that the background of this slide has kind of the home screen of the web page. So on the right, there's a menu where you can open up and click on the different imagery that's available. So definitely encourage you to take a look at that. And if you have any questions, just like Robin, I have a NOAA email address as well. So it's amy.huff@noaa.gov. Please feel free to reach out. All right, thank you.
Thank you so much, Amy, for that great presentation. It made it really understandable for folks who aren't experts on satellites like me. So we have some questions rolling in. Feel free to please keep adding them into the question box if you have them. The first question is, I think this is a callback to an earlier slide. Why does the VIIRS image have no pink or magenta at the fire itself, where smoke is likely the thickest? Yeah.
Okay, that is a great question. And it happens not only with, this is the aerosol detection product that the question is specifically about, it also happens with the aerosol optical depth product as well. And so the reason is because these algorithms, these scientific formulas essentially that are used to retrieve the aerosol products, one of the things that they have to do is first identify where there are clouds, because clouds are very reflective. So any place there's a cloud, we can't retrieve the aerosol products, either aerosol optical depth or aerosol detection. So the very thickest smoke will be mistaken for a cloud by these different aspects of the algorithm that are used to identify clouds. So the reason why we don't have any retrievals in areas where they're the thickest part of the smoke plume often is because the algorithm thinks that that is a cloud. So that is kind of a known, that's just not NOAA products. That's like every agency's aerosol products. It's unfortunately, it's a known limitation. And there's a lot of research that we're doing and other groups are doing to try to, come up with ways to identify when that happens and then go back and be able to fill the gaps. So that's an area of active research. And unfortunately, that is one of the limitations that if you're using satellite products, you just have to be aware of. Yeah, that's a great question.
Great, thank you. And the question asker thanks you as well. um, we have another question. I'm not sure if you'll have the answer to this, but the question is,
Okay.
will NOAA have access to FireSat satellite data when it comes online?
I don't know the answer to that, but I can certainly find out.
Great.
So I'm a member of the aerosols and atmospheric composition science team. So I'll reach out to my colleagues on the fire science team and find out. And then maybe, I don't know, Clara, can we maybe send out an email or something to let people know?
Absolutely.
Or maybe
Yeah,
we can contact that user. Okay.
I'll get you connected. Yep.
Okay, great. Thank you. I'm going to make a
Great.
note of that.
Okay. Another question, once you're ready, talking about smoke, how does smoke influence the ability to detect and follow fire spots and lines?
Oh, so in terms of the fire detections, so let me go back to
Yes.
So actually, the fire detections, the algorithm that detects the fires and then calculates the fire rate of power, it uses different wavelengths. So again, I'm not a member of the fire team, but my understanding is that the actual presence of the smoke is not interfering with the ability to detect the fires. But again, I can double check on that and also, get back on that as well. Or maybe Robin might actually have the answer to that as well.
Great, thanks. Another question, Robin, do you want
Oh,
to
yeah,
weigh
let
in on
Robin
that?
answer.
Yeah.
Yeah.
Sorry, I keep going on and off of camera. Yeah, so since we are detecting thermal imagery with the fire radiative power, we can typically see that outside of clouds and those types of impacts.
Great,
Yeah,
thank you,
super great.
Robin.
Thanks, Robin. So yeah, so I was right. That's good. That's a confirmation. So there are different wavelengths that are being used from that the satellite is measuring to detect or to show the smoke versus detecting the fires. Awesome.
And actually, if Robin could stay on for 1 second, we
Okay.
have a question that I think is relevant to both of you. We have a question, which of the products you mentioned are used for the fire spot detection mentioned by Robin? Is there anything else you'd like to add about that?
So it is the fire radiative power that we're showing on here, but it's then post-processed into a more user-friendly system that's called the Next Generation Fire System that NESDIS has created. And it is both a mapping feature as well as a table of tabular details on the location. And that is the new technology from NESDIS that Weather Service Office forecasters can access to be able to monitor new fire starts in their area of responsibility, as well as be able to proactively generate a site-specific spot forecast for that location and send it to partners.
Great. Thank you so much. And thank you, Amy, for your presentation. I think we'll move on now to our next presentation. So let me. This is going to be, we're going to hear from Fenglin Yang next, and I'll allow Fenglin to share slides. So Fenglin Yang is the National Weather Service's Environmental Modeling Center and National Centers for Environmental Predictions Division Chief for the Physics and Dynamics Division. Fenglin's presentation will cover performance of NOAA's operational air quality and smoke forecast systems during the January 2025 LA wildfire events. Thank you so much for being here, and go ahead.
Thank you, Connor. First, I'd like to thank all the organizing committees of this webinar to give me this opportunity to present our modeling work. And so my title is Performs NOAA Operational Air Quality and Smoke Forecast System during January and air wildfire events. And first, I'd like to thank all the developers of this for our models, and also this definitely is a collaboration between EMC and also AR labs, including AR, GSL, CSL, PSL, and also including NESTIS, and also a few universities. So this is the outline of my talk. First, I'd like to introduce to you the EMC and our unified forecast system. And the second is about our operational models for fire predictions. And then the evaluation of the area fire forecast event. And finally, about the challenges and also our ongoing work. So these are National Weather Service and National Center for Environmental Prediction and Environmental Modeling Center. We develop and implement the prediction systems that provide operational numeric guidance and current different spatial and temporal scale for use across the NWS and also worldwide partners. And you can see we have many different modeling suites. Currently, we have 38 different models in operation, uh, spanning from dispersion modeling up to like seasonal ENSO forecast. In the past, we have been developing the models independently, starting from about 5 years ago, we switched to a so-called unified forecast system. Under the same infrastructure, you can have different applications, and this infrastructure supports fully coupled assessment model. It has many different components, including ocean, wave, land, sea ice, space, and of course also air soil and air quality forecast application and the atmosphere physics and the dynamics. So on the lower left, list some of the component models currently included in this assessed model. On the right-hand side, on the regional applications, we have the hurricane forecast analysis and the forecast system called HAFS, an air quality modeling application, and also the regional weather forecast called RFS. On the global side, we have the GFS, SFS, and the GIFs. They are all fully coupled Earth system model with ocean, ice, wave, land included. And we also have the answers only like for space-based application called one model, also the global chemistry and aerosol forecast system. In terms of air quality and wildfire prediction systems, currently there are 3 different models running in operation. The first one is called UFS air quality modeling AQM. It covers North America, has 13 kilometer horizontal resolution in the vertical 64 layers. It uses the EPA developed CMAC air quality model and coupled with the gas phase and also aerosol modules. It uses the latest developed wave fire emission and also the plume rise use of air and also have different anthropogenic emission inventories. The forecast extends to 72 hours. It runs 4 times per day, but it's only for the extended forecast, 72-hour forecast is only 60 and 12 days. We have also a very high resolution 3 kilometer North American and Alaska domain called HER smoke model. It does not include any chemistries, so it mostly like run as a tracers. it does include the emissions from wires and bodies using fire reduced power. In terms of plume rise, it uses phase plume rise. It runs 4 times per day for the actually it's hour cycled, but for 2-day forecast, only for the synoptic cycles. We also have this global aerosol forecast system. It's one of the global ensemble forecast system called GIPS aerosol. Much cost resolution, 25 kilometer and 64 layers. It uses a go-kart aerosol module. It has simple gas phase chemistry, and also it uses a different emission, fire emission called GBB EPX, also developed by Nestes. The forecast extends to 5 days, 120 hours. We're quickly showing a more straightforward or what the domain coverage is. Here is the AQM coverage for North American domain. The products are only made for the Alaska, Kansas, and Hawaii region. It's fully coupled with the atmosphere, so it's very interactive air quality forecast with the meteorology. And the first version of this interactive UFA space system was implemented last year in May, and later we made a minor upgrade. And for the HER, and actually it all has a ramp. Ramp is a much cost resolution ramp smoke. It provides the natural boundary condition for the HER smoke. HER smoke runs over Alaska and also Kansas region. It is 3 kilometer resolution. Primarily developed by the GSR, also getting implemented with GMC into operation. And so previous speakers have mentioned about the airfare, and like this is shows again the airfare. There are 2 major fires, Palisades and also Eaton fires. You can see this showed earlier actually. Maybe this sentinel image for this fire event from Nestes. So also mentioned by previous speakers, the fire is a major hazards. In the past 2 decades, the air fire is one of the largest. In terms of the cost, it's not just fire event and also has a lot of fatalities. So for this fire event, in terms of meteorology, why there's the cost of the fire event, a few factors contribute to this fire event. So it has a very strong Santa Ana wind. It's very dry because this wind also the wind speed up to 99 meter per hour, so it's very strong wind, and coupled with very low humidity and also high temperature. This animation, the forecast from air quality model version 7 in operation, this a particular utilization from January 9th, 12th utilization. So you can see it captured overall the wildfire plumes. So what being used here, the fire emission is a regional API and various emission version 2 called REVO. And the forecast I already mentioned, the forecast up to 3 days. And the circle for verification circles are from the EPA air law observations. So if we compare the three models, AQM I mentioned earlier, our regional air quality model and gives the global ensemble global model, and also the HER very high resolution HER prediction. Overall, the AQM gives both over predict the PM 2.5 concentration near the fire source, while the HER under predict the smoke concentration, primarily because the HER did not include the fires in the urban region. This is evaluation, and so we have this subdomains for evaluation, and on the right-hand side is over the entire Kaunas region, we have the air line observations, is this blank line. Our operation model is a red line. You can see capture overall the time evolution in the 1 week of also the fire event. Definitely can say the over prediction or then the generate the lines by the AQM. But the other models, as a HER, underestimated um, the PM 2.5, while on the global model, they give sometimes, most time is lower estimation, but there are also a few good forecasts. Zoom into this West Coast region, you can see the same thing. The AQM capture most of the event, but it has not overestimate on generally the lines, and also has a peak of the shift because we have to use the emission from day early, and we don't have real-time emission. And also the HER underestimated this PM 2.5 for this event. This also verification over the fuel stations. Airlock station is Long Beach, and this Santa Clarita, and also Area Main Street. The same story overall, and the AQM overestimated the event, but the HER underestimated the PM 2.5. So a quick summary about the area fires. I would mention it's a lot of damages in terms of the property loss, and also has 28 fatalities. In terms of meteorology, the cause of the wildfire is the strong Santa Ana winds and the dry weather condition, and also high temperature, that driven the ignition and also rapid spread of the wildfires. NOAA 3 operational model are examined to assess the impact on smoke and the PM 2.5 prediction during the fire events. The AQM and the global model overpredicts the PM 2.5, while the HER underestimated. Probably overall, all the three models were able to capture the spread of the smokes after the fire events. And some of the challenges, I think the weather model has the biases. We need to further to improve the representation of the fire emission and how they are being used in the model, and also the refinement of the plume rise algorithm. We still have ongoing work. There's a new RFS and regional temperature refuge forecast model and coupled with smoke and dust that will become operation hopefully in early next year, and can improve the smoke and the dust prediction. For the regional air quality forecast system, we have the version 8 under development. We're going to upgrade the chemistry model CMAC up to version 5.4. We'll also improve the meteorology forecast by updating the physics package to the GFS version 70 physics. We'll use the newer the anthropogenic emission inventories, also use the REV and VOC emission. We plan to increase the model resolution from 13 to 12 to 9 kilometers. That's to be determined. determined. And we're also working on the data simulation, use the GDAT-based data simulation to simulate chemical species to constrain chemical ideal conditions, and also improve the vegetative sub-canopy effects in the air quality forecasting. In addition, we set up a new model called Global Chemistry and Aerosol Forecast System, and the plan to implement it for operation next year. The first version will have the GDI aerosol data simulation, but only have the aerosol, gas phase and heterogeneous chemistry, but that will be follow the first implementation in FY26. Just give you a heads up, very early result, but the ACM version 8, this beta version operate. I mentioned earlier, our ACM overpredict the PM 2.5. In this newer version, you can say reduce the PM 2.5 on biases in this air fire region. That's all my talk about it. I want to point to a few websites. The first one is our ACM data. It's available on the cloud, also on NOAA server. And we have the NWS and ACM forecast guidance based on our numerical model forecast, and also the latest experimental RFSSD forecast also available on the website. Thank you.
Thank you so much, Fenglin. That was great. If people have questions, feel free to put them in the question box. We can start off with a question about the dissemination of this forecast. How is it disseminated in particular for the LA fires, and how did the information flow, and how was it used?
So that's good. On the last on the slide on the screen, we have the NWS forecast guidance website. Anytime all the forecasters, actually it's being widely used by the state and air quality forecasters, and they use this website all the time. I believe at that time the forecasters did use information from this website.
Thank you. Another question, do you expect the underestimation of emissions to be a problem in the future as more structures burn rather than forest and other wildland?
I think for the underestimation especially for the HER, it did not include the urban sources. That will be a consideration for the HER, but for the AQM and the GIFs, and I think we have a over prediction, and that's more about the polymerize and how the emission source being used in the model.
Great, thank you.
I just wanted
Robin?
to add on that from the fire community side of things. That is an area of emerging research with regard to using structures as a fuel type. Typically in fire behavior modeling, fuels are considered vegetative types. And so now trying to model fire behavior as it moves through a community is a very much emerging area. And of course, that would impact and influence our side and the NOAA side with regard to coupled modeling with that fire behavior.
Yeah, I want to add, Robert, thanks for that. And all the models I mentioned today, we do not have any fire behavior modeling coupled to it. You can say the emissions are all prescribed. If we wonderful, we can model the fire behavior and provide much timely emission instead of have as I mentioned earlier, 1 day delay of the emission.
Great. We have one more question about the HER forecast. Does the low HER forecast imply that the regional urban pollution source is larger than the fire smoke?
I think it's the burning of the urban structures because the area fire is not a burning of the cars, houses. Those sources, I think, were not included in the HER forecast.
Okay, gotcha. All right, so in the interest of time, I think we're almost out of time for this hour, and we'll wrap up our webinar. So thank you so much to all of our speakers today, and thanks to all the attendees. Just as a note about this last topic we were covering about fires at the wildland urban interface, we are planning to have a webinar further on in this series that focuses on that topic. So if you're interested, there's a link in the chat already where our future webinars will be posted. But coming up on August 6th is going to be our next webinar, and it'll focus on fire and land atmosphere interactions and specifically improving models in that area. And we're going to hear from some NOAA colleagues from the Geophysical Fluid Dynamics Laboratory. So thank you on behalf of the Climate Program Office and the Forest team. We hope to see you for future webinars in this series. So I put a link in the chat, as I mentioned, where you can find the future webinars and past recordings of webinars. And feel free to please reach out to me if you have any questions or suggestions for this webinar in general. So thank you very much. Thanks for joining and have a great day.